here. I don't know if I will tell you everything, but I'll at least try to tell you something. So yes, the title is. Oh, before I begin, I should mention, if you have any questions, please interrupt and ask. It's not essential that I actually finish my talk, as long as I can give you some interesting information, or I can interest you a little bit about what we are trying to do. So this is the title, three-dimensional within bracket super. There's a reason for that. We cannot completely say that it has no. I mean, supersymmetry has no relevance or no role, even though the role seems rather minor or technical. Three-dimensional Yang mills with compressible quark matter, and for my purposes, this word compressible essentially means that you have finite density. The density is non-zero. That is all it means.
The three, just to make sure you're counting like particle physics.
I'm counting like, yes, that is indeed a very good point, and it caused us a lot of pain because at some point of time we needed to rewrite the paper in a particle physics notation, and it completely threw us off because there was one missing everywhere. Every time we proofread, there was somewhere a factor of, not a factor, but an addition of one missing. Because yes. So by three dimensions, we need 2 plus 1, 2 space, 1 time. But for a large part of the story, I'll also tell you a slightly generic story, which is not just 2 plus 1 dimensional. It's valid in all dimensions. And I should begin with some credits. So what I will try to describe today is primarily based on these two works and some works in progress, as always, and with collaboration, in a collaboration with Andon, David, Veneziano, and Javier. All of them are currently at Barcelona, where I was also a while back. So, right. Let me start with a very brief outline. So, what I will try to do is I will try to give you a short motivation and introduction. Why we at all care about finite density matter, and not just that. We also there's also this factor of strong coupling, and this is precisely this phrase that finite density matter at strong coupling. It's where things become very very complicated, and we have very very few tools to actually address such questions, even though these are very physical to begin with. Then I will try to motivate you or give you essentially the framework in which I will try to address the question. And the framework would be gauge string duality, which is more commonly referred to as gauge gravity duality or holography. And specifically speaking, I will also include some contributions of fundamental flavors. In other words, objects like quarks. So that will be a very key ingredient. And I want to view this duality. I mean, there are many interesting things about this duality, and you can take various different viewpoints. But for my present purposes, I just want to see it as a framework of studying quantum field theories. So if you like, it's again garden variety quantum field theory that we are studying in disguise of a slightly more complicated or dressed up version. And there's a reason for that. I could have actually switched the order of these two. I could have given this as a motivation and that as an application, but anyhow. Then, within this framework, I will try to tell you a general story with non-zero density. And when I say, I mean, there's a subtext here. I'm saying that, declaring that I will be talking about things up to 5 plus 1 dimensional quantum field theory. But this 5 plus 1 dimensional case specifically is a little problematic. So if you really like, let's just consider up to 4 plus 1. In other words, 5 dimensional quantum field theory in particle language. So that's a general story. There is a general story. And then I will try to focus on a very specific model, which is 2 plus 1 dimensional, or 3 dimensional in short, quantum field theory, which is asymptotically free. And in there, we will what we'll try to describe is what happens if you have non-trivial flavor physics in presence of a non-zero density and back reaction, etc. All in this gauge gravity duality, all in the context of gauge gravity duality, etc. And then I will conclude with some general remarks, some future directions, etc. etc.
And this is really terrible of me. But the reason you don't want to do 3 plus 1, even though we can do Sakai Sukumoto, whatever, is that there are some technical problems there.
There is usually you run into the Landau hole kind of problem.
The UV stuff gets you.
The UV stuff gets. I mean, it's not like you cannot do it. I mean, you can. With the cutoff, you can certainly do that. But this is actually a much nicer example in the sense that if you are in 2 plus 1, the UV remains as it is. So, I mean, you are fine as long as without. I mean, if you believe the story without flavor, with flavor or density doesn't destroy that at all. So
it's not the real world. So
yes, I mean, certainly. I mean, as I said, it's a framework of studying quantum field theories, and then you study various examples and try to understand as much as possible. So that's roughly the outline. Okay.
Since Shiraz just walked in, give him a brief.
Yes. So I just started with by saying that this will be a rough outline of the talk. I'll start with some motivations about what happens to finite density matter at strong coupling. And when I say finite density matter at strong coupling, I really have in mind some quantum field theory, studying some quantum field theory at finite density and strong coupling. And the framework in which I will try to do that is essentially this gauge string duality or gauge gravity duality or flavours, whatever your favorite phrase is, with the inclusion of fundamental flavors or quark-like objects. And in there, what I will try to tell you is there is a general story at non-zero density up to a 5 plus 1 dimensional quantum field theory, but really the 5 plus 1 dimensional case in itself is a little problematic. So if you like up to 4 plus 1, this is much better understood. And then I will focus on a very specific model, which will be a 2 plus 1 dimensional case, in which you have asymptotic. It's an asymptotically free theory, and in there, what we will try to understand what happens if you have non-trivial quark or flavors, and then some finite density, and then everything back reacts, and what happens inside, and then conclusion. Okay. Any questions? If not, then sorry. Let me give you a little more concrete motivation, if you like. So this is there's a very good example. If you look at the phase diagram of QCD, and by phase diagram I really mean that this is a proposed phase diagram. This is not actually what is experimentally observed, although people believe that various phases that are mapped out here. I mean, there are robust arguments for them, so people do believe that these are indeed phases of UCD. And it is an incredibly rich phase structure in the sense that there are various phases. And what I really want to focus on for motivational purpose is this right-hand corner, which is called the superconducting phase or superfluid phase. But there is some the technical word is that this is a color superconductor. And this, by the way, is a conjecture. It has not been observed. What people expect or hope is that you might be able to see some features of this in possibly neutron stars where the density is very high. So this is a phase which is conjectured at very high densities within QCD.
The basic thinking is that whatever, I forget now, but color, octet channel or whatever, there is some pairing.
There is a PCS pairing which basically is the leading mechanism that drives you towards condensation, something like that. And
CXL is the color flavor.
Color flavor law, yes. Color flavor law, yes. Right. So this is again this is a reasonably good motivation.
And asymptotically high densities, the calculations are reliable.
The calculations, yes. You can show prove. You can prove, yes, indeed.
I think that's where you do this one gluon exchange and you get in some channel.
Yes, indeed.
What is the difference between 2SC and CFL?
Maybe I should not have shown this. Can I request you to ignore this for a moment? Because I really want to use this as a motivation. I'm not going to even claim that we have anything even close to this. This is just I'm just trying to motivate you that there is a very interesting case, which as Shiraz was pointing out, that you can convincingly argue or show or do within QCD or QCD-like theories that it has to exist for asymptotically high densities. And this is something which we have not seen yet in a lab, if you like. So the take-home message is, or the take-home motivation from this slide is that there could be interesting things happening at finite density and strongly coupled state. Okay, so one other point I can make at this slide even is that it is correct that at asymptotically high densities or asymptotically high chemical potential, we can do a perturbative field theory analysis to argue that such a phase should exist. But we don't really know what should happen if the field theory is strongly coupled, if the description is strongly coupled. Because at asymptotically high densities, you can do a perturbation.
But in QCD, it's self-consistently weakly coupled that happens.
Yes. Okay, so as I said, this is a good motivation to complete phase diagram of QCD at finite density, and especially if you like, because nothing like this has been observed, although strongly argued to exist, this color flavor lock phase. And in general, if I forget about QCD, this is a question in quantum field theory that I can ask, anyone can ask, is what happens or what is the ground state of a strongly interacting system at finite density? So completely generic issue in theory. The problem in addressing such a question are that there are technical limitations. Specifically speaking, for example, in QCD, a lot of strong coupling features you can address by doing lattice simulations, which you cannot do at finite density because of there's a very infamous sign problem. In other words, you have to do a simulation and that has to convert somewhere. If you have finite density, it doesn't convert. So there is a problem, you cannot really calculate. So then, what you instead want to do, if you can come up with representative soluble models on which you have sufficient handle, sufficient control, whether you can address such questions in those cases. And as I said, that I'm just going to view this duality, this gauge-string duality, as a framework for addressing such questions. It's just a toy model, if you like. All right. Excuse me. So there's a further motivation. So if you take a first step, you can immediately argue, because this gauge gravity duality works at large n, you can immediately argue, as people have, is if I have a theory like QCD, at large n, this color flavor locking is suppressed. Instead, what is favored is something called a chiral density wave. So your immediate conclusion would be that you should not be able to see such superconductivity or color superconductivity at large n, because this pairing is completely suppressed by factors of 1 over n. So I should not see them. However, as subsequently shown by Schuster and so on, is that you could, just within QCD, you could do a high density perturbative analysis, and in there, what you would find is that color flavored log phase happens if the number of flavor over number of color exceeds this bound, which is sufficiently small, but it has to be bigger than that.
This is just in QCD.
This is just in QCD. So, and indeed, in QCD, this bound is satisfied because it's not, NF is not negligible compared to N. So, their argument was that, if I want to understand QCD at large N, I would never see this phase, and they subsequently, these people subsequently argued that that is true as long as you don't take any flavor at all into your picture. But if you take flavors, the story changes. So, in other words, for us, the motivation I want to take from here is that if I want to see such a phase, just based on this observation, perhaps it's important to take a back reaction in the geometry, because I'm going to talk about everything. I'm going to talk in terms of geometries. So what we really need to do is take back reaction, and in a preferably controlled way. So this is what gives or leads us to something called a Veneziano limit, which is like a Thuk limit, except that you have color and flavor both, and you take both of these numbers to infinity, such that this NF over N is fixed, and this is a tunable parameter in the theory. So Thuk limit is when there is no NF, essentially. In other words, this fixed number is
Yes. So I thought that initially, this color flavor locked objects were like singlets made out of some SE2 color and SE2 flavor or this U3.
They are not gauge singlets.
No, not gauge singlets.
Oh,
Just
okay.
Yes, it was what? No, they were not gauge singlets, of course, because I'm thinking. I thought that they were the same gauge, but that's probably not.
It is for 3 flavors and 3 colors. Delta IJ or
Yes.
something.
Something like that.
Yeah, I needed to. So this is okay. So, but clearly there are generalizations in which NF is hugely smaller than.
Yes.
Yeah.
Even the original story, I think they also dealt with 3 colors and 2 flavors.
Oh, really?
And it was significantly, the qualitative difference.
I see.
Okay.
They just choose the 2 SU2 of SU3 color, right?
But I remember that the phenomenology was significantly different.
I see.
Okay. Any other questions? If not, let me go to this slide. I don't really have to explain this, but I just mention what's in there. So evidently we have to resort to some version of holographic gauge gravity, whatever. And these are the stringy ingredients. You have a bunch of DP brains sitting at the tip of a cone, typically speaking. That's how you get this sort of structure. And this is just an example that if I take a bunch of D3 brains on the tip of a cone, which base is a Sasaki-Einstein or an Einstein manifold for that matter, typically you would end up with a quiver type gauge theory. And the geometry corresponds to, or the dual to that is essentially is 5 times some compact manifold, which would be Sasaki-Einstein or just simply Einstein if you don't care about supersymmetry.
But the simplest thing is just to do the Witten construction, right? And put it on a thermal circle, which you then regard as some internal space, some Briggs Suzy.
Oh,
That's
yes,
not what
yes.
you want.
That's not what I'm doing. I'm not doing that. That's not what I'm doing.
So you have this, sorry, just to anticipate,
Yes.
you'll have this, cone and so on, and then you'll put in the flavor grains and then take the back reactions.
And then, of course, I mean, everything at the end of the day, you're just focused on the near horizon event. I don't care about what's happening as well. Right. So, and adding flavors is this is also standard. But I'll just mention if I take this example of D3 brains and the background geometry, if you like, is made of n number of D3 brains, and in there I'm just adding some nth number of D7s. Then what happens is the caricature of the cartoon is roughly like this, where this extended thing is a D7, the small thing is a D3. Just to make clear the larger dimension. D7 is the one with the larger volume, if you like. And you have essentially 3 kinds of strings, three strings, which give you that joint sector, which was there, just from these pieces. And then there will be 3 7 strings, which are essentially giving us the fundamental matter, the quark, in other words. So we have to have such a configuration, and typically in literature what people do just for simplicity is take these brains as probes in a geometry. In other words, these brains will be probes in this asymptotically it is 5 times whatever geometry. But that is not what we want to do. We want to go beyond the probe approximation to see what happens. Okay, so a general story, that was a specific example. You can do the same thing with in general DP brains, where P is less than 5. You can also take P equal to 5, but that's as I said, is a problematic case. You can leave it out. You can do the mathematics if you like, but physics-wise it's usually problematic. So if you like P less than 5, and essentially what you get, the field theory, the dual field theory is some SU and Yang-Mills theory, and it could be supersymmetric. Depending on what configuration you start from here. And typically the description wherever it is valid is or can be given in terms of supergravity. And essentially the background that you get would be conformal to some ADS-P plus 2 times X8 minus P compact manifold, which is usually Einstein manifold, but you can put in more structure if you want to have supersymmetry like near Sasaki or nearly Kähler, depending on the dimensions, etc. So this is basically the adjoint sector of the theory, if you like. And the fundamental degrees of freedom are added into this by having a dp plus 4. So if I have a dp brain, I'm just adding dp plus 4 flavor brains. So these are adding fundamental degrees of freedom. And the way I'm adding this is as follows. They essentially wrap this entire ADS part, conformal ADS part, times some three directions inside this compact one. Of course, I'm assuming that such a configuration exists.
See, so okay, this is so for the 3-brane case, you actually have the 7-brane filling the three dimensions and the radial direction, and then Rabita. Why that radial direction is a bit strange? I don't know.
That is because you want this to be you want the gauge group on the D7 branes to not have any dynamics. So if you wrap the radial direction, so basically the gauge coupling kind of freezes the dynamics. So it becomes a global symmetry.
I guess this is what Sakai Sugimoto in one.
This
does
yes, the D4DA
D8 also goes in.
Yeah.
But I think you think it's this way. Suppose you think in flat space. There are the D3 branes and the D7 branes. There's some distance away, let's say, from the D3 branes. Now the radial coordinate is a distance coordinate away from the D3 branes. So there is a D7 brane and every distance away from the D3 branes, larger than a certain brane. Which means that the D3 branes, the D7 branes in the near horizon geometry will fill out or will appear in all radial coordinate above a certain point. You see what I'm saying?
Yeah, but I was just okay. There's another possible configuration where the D7 did not.
But the D7 and D3 share common world volumes, and then there are some 4 extra transfers.
And
so think of all the D3 directions as like a point.
Okay.
So there's a point and there's this other thing. And the radial direction in ADS is just how far you are from this. So because this is going like this, you're at every distance, which means you must be going all the way to R equals infinity. But starting from a minimum, you don't need to go all the way down, and that minimum will give you the mass. And you wrap an S3 basically.
You wrap an S3.
Because you're going to preserve something. You're going to preserve the right symmetry.
Okay. And then the idea here is basically just essentially generalize what Shilal was saying, including back reaction. In other words, it's Veneziano limit at this number of. So these flavor branes are no longer just probes; they will also change the geometry. The question is what will happen when they do.
This is what happens again. The thing comes in and goes out.
Yes, right? That is one where parallel symmetry broken, etc. All those things. And I said I would consider finite or non-zero charge density. Often finite, by finite I mean non-zero. So let me just say what that is. Essentially what happens is the understanding is as follows. The way you understand the charge density is you take this probe branes, or they are not going to be probe, but suppose I start with this probe branes. And on that probe brane I excite some U1 gauge field of this form. Basically has a radial profile, if you like, and a time and the leg along the time direction. You can show that for all these cases, for all the cases that I described here, the details are irrelevant. The asymptotic fall-off condition with a proper definition of asymptotics, of course, sometimes we need to put a cutoff here, is going to be this. It's going to be this, where this non-normalizable mode will correspond to a chemical potential, and the normalizable mode will correspond to the charge density. So this is what the charge density corresponds to. You can also argue that so this is what is happening at the level of a Dirac-Born field action, because that's what describing the dynamics of the probe. What you can also argue, actually precisely, is that there is a sense in which you can take a large charge limit, where this entire Dirac-Born field action will just give you a bunch of Tango-Goto action. In other words, if I have a very, very large charge on the brane, I can replace that configuration by a bunch of strings. That would be one limit. And that's what it is written here. So that would be the state number 1. We want to replace this flavor plus flux configuration by an explicit external string sources.
So one description is you have the flavor brane with a lot of flux on it.
Yes.
And the other is that you just have strings going between, say, the 3 and the 7 in that.
Yes.
Just classical strings?
Classical strings. Pure classical strings.
Now you're using somehow the electric field on the 7 brane carries string
charges. Yes. Exactly. And in fact, precisely this rho, this is the electric field on the 7 brane, if you like, or whatever brane. This rho is going to be related to the number of strings here. When you take this,
the flavor brane description one where you smear the charge, the strain charges out?
Yes.
Doesn't it make a difference? I mean, we are finding a particular classical solution with that.
So I would argue that it would not, in the sense. So maybe it will become clearer because this is one limit in which the problem is simple. So our goal is now to start with a simple enough situation, which is at least solvable.
You're just saying there's a mathematical equivalence, right? That you start with a number, go to equivalence.
Yes.
Theory, you put on a lot of electric flux, and this is the same. You can just show a mathematical.
Yes.
That this is the same. The back reaction is the same as.
That's right.
Because purely coming roughly from the string charge.
That's right. Yes.
And then you smear out the string charge.
That's right. That's right.
How?
That's right. All you have to do is so there's a technical thing which is I don't think physically relevant, but all you have to do is when you take this limit, instead of working with the DBI, you have to take a Legendre transformation of the DBI and take that limit. And you can show that essentially that Legendre transformed action basically is just proportional to a number over action up to some over factor.
I still don't understand. I have the same question as Sandeep. So these are the scalar nullness in a spikes configurations. On the
yes.
So they are localized.
Not yet. So I'm actually going to localize in what
You have to. I mean, these spikes are located. Along. So if you're thinking of the D7 branes, then
yes.
the spikes are somewhere. So there's one spike, two spikes, three spikes,
etc. Not. I'm not sure about what you are referring to, but the one I'm describing or trying to describe here is that I have a D7 brane which spans basically all the spatial directions. Let's just say that, and I'm going to replace that configuration by a bunch of strings which are also smeared all over the space.
Your spikes got them at the positions of the charges.
Yeah.
He doesn't have free charges. His charges are at infinity. He just has a flux.
But
the charge density
number what the action for the
so the charge then makes a string which comes into ES. So there's no charge in ES. The charge is just at the boundary. So it's just it's just like a Wilson loop. It's just like a Wilson loop.
But am I not breaking this symmetry or homogeneity?
I think it's smeared the string.
Smeared everywhere. Smeared everywhere. That's how you preserve homogeneity. Otherwise, you break it. Yes.
So it's like a density, like a charge density of strings.
Indeed.
So eventually, in the calculation, only the density will appear.
Yes, indeed. And that is going to be almost my next point. Is that so the system that you have, and I see that I'm doing except.
We're not very strict about that.
Okay, good. I also said that it's not necessary I have to actually finish it as long as I can convey something.
It's usually a game of who loses patience.
Okay, so this is going to be the total system, if you like. So you have supergravity type B, depending on the situation, and you have a bunch of strings. And then, as you mentioned, that typically the strings will act as localized sources, and I will end up with a Hornbus set of coupled nonlinear PDEs, which I will not even attempt to solve, or pretend to solve rather. So instead, what we are going to do is as follows. So suppose I have this DP branes, and so there's a time direction, there's a radial direction, there's this P spatial directions along with the PQ radius, if you like, and then there are compact directions, 8 minus P compact directions. And what I'm going to do is I'm going to take fundamental strings which are spanning along this T and R, and I'm going to smear them all over the spatial directions and all over the compact directions as well, which will simplify the problem completely. It will just give me ordinary differential equations.
And that's what you're supposed to. Because the original DP brane, your sources at infinity were smeared in this way. So the electric field will come smeared in this way.
Yes.
It's not even an approximate. I mean, this is the right thing.
And then, so you could still consider, for example, the probe branes which were only localized in a submanifold of this, right? Because they are wrapping only a submanifold of it. I mean, they are not extended.
I think you're saying that we know from physical grounds that all the charges are homogeneous in the physical space.
Right.
But we don't know how they localize in the auxiliary space.
Exactly.
But here you're assuming that they
Exactly.
Yeah, it's a little bit like this instanton modulus space, whether you think of very small instantons or you think of them as dissolved anyway. And people assume equivalences in various results.
And what is the statement that if you had been able to solve the original problem, where you had the flavor brains localized, let's say, with back reaction, then the smeared version of that problem is equivalent to this one?
So there are many smearings. So first of all, of course, when I'm talking about this flavor brains, they don't span the 10 dimensions. So they have to be localized in some.
Yeah.
So even if they are localized in, let's say, if it's a 4-dimension 2 system, then I already have a partial differential equation to solve, which will be hard. So what I will instead do is I will pretend that I have a lot of flavor brains, and I'm going to smear them all over the transverse manifold as well. So that will recover all the symmetries of the 10-dimensional background. They will just become some, I mean, if you like, this is like an S-square approximation of doing, I don't know,
spherical shell of these surrounding the leaf.
Exactly. So it's not the original configuration or the ideal configuration you would like to solve.
But that's what I was asking, that the smeared flavor brain solution is in a mathematically precise way equivalent to the fundamental string smeared solution. Is it?
Yes, that
up
is
to
correct.
some Legendre transform.
That is correct.
But I think more must be true. That is, the single flavor brain, I mean, localized flavor brain solution must also, in a mathematically precise sense, be equal to the smeared fundamental string solution.
Smeared, yes.
Smeared in the limited spheric sense.
That is correct.
You know, it's just like you've got a particular brain, you've got flux all over it. So since you've got flux all over it, you've got string charge all over it. And that string charge dominates the whole configuration. I think it's all it comes.
Single flavor brain, but must
Single
be-
meaning n of them, but that's at one point. So, I mean, let's say we're not smearing the flavors. Because these 3 brains are the origin. We've got the 7 brains here. We put lots of them. Okay? But, you know, not in a spherical shell. Okay? Now that's still in many directions. Extending many directions of the D3 plane and many other directions. And then the configuration, you're assuming that the dynamically favored configuration carrying charge is one in which the electric field is uniform over the D7 planes. So that smears out the string charge in the localized, in the directions of the 7 brains without necessarily requiring you to smear the 7 brains themselves.
But still, only in the limit where the charge is
Very, very large. Yes.
Yeah, because then most of the back reactions dominate by the charge.
Exactly.
By this time. There are 2 charges, you're looking at the limit
The
of this
7
charge.
brain
dominates
charge
the second.
is
Exactly.
not so bad. Then I agree.
And then the statement is, when I start to go away from this extremely extremely large charge limit, there's a consistent story you can build on the story that you have here.
But by the way, the S-dual description, where the fundamental strings, let's say we did type 2, the fundamental strings are replaced by D strings, then you could really look at the world volume theory of the D strings.
Yes.
And then there is really a non-commuting configuration that builds up the 7 brains.
Yes.
Out
Yes.
of that.
Yeah.
You could do this you could keep track, you could perturb including the 7 brain charge.
Yes. That is true.
That would be hard to do from the fundamental string, right?
I think so, yes. I think so. Yeah, I think it might be, yeah. Okay, so just a couple of words on smearing and what does it do. So, of course, first of all, by smearing, I mean this smearing, that everything, on the compact manifold, nothing is localized, everything is smeared. So, obviously, first thing is that it's very convenient because it allows us to.
This is the smearing of the G7 brains.
This is the smearing of the, if you like, this is smearing in the compact part, not in the configuration space, but in the.
But just to understand, the smearing of these, like
Smearing of the
D7 brains.
D7. Yes. And as I said, that it's like it's an approximation in that, if you are particularly fan of that.
It's an approximation because it would not be supersymmetric. Or would it be? I mean, could one consider the case where we had D3 brains and D7 brains smeared really located in a slightly symmetric configuration around the D7 brain? That would preserve supersymmetry still?
So if you're asking, for example, whether there are there are ways to smear D7s which preserve supersymmetry.
Yeah.
The answer is yes.
Yeah. So then, in the particular case of n equals 4, this is not even an approximation. It's one particular value.
Yeah. Certainly. By approximation, I'm just saying the particular configuration. Yes, indeed.
Yeah. One particular thing.
And yes, and that is essentially the next statement, if you like. The specific smearing essentially fixes the quantum numbers for the force, if you like. So it's a particular field. A further approximation, if you are extremely critical about this, is that in order to smear, you have to take a continuous distribution. You have to take not just large number of flavors, but you have to pretend that they are also continuous, and it's in itself it's an approximation, although it doesn't really bother us fundamentally.
Yeah, it's an approximation justified by 1 over n.
Justified by 1 over n.
So this is surprising that the supersymmetry is. I mean, I would have thought that if the D7 brane is here, then there's a particular set of supersymmetries which is preserved, and then when you take it somewhere else, there is some. But maybe they are all.
No, there could be a common supersymmetry, but so for the D7s, I should now be a little more careful because for the D7 case, I don't remember an example. I'm sure there is one. But what I actually will talk about is the D2, D6 system, if you like. So the adjoint sector is the D2 branes, and then on top of that you have D6 branes, which are going to back react, etc. And there are configurations. There are smearings. There are ways to smear D6 branes. Which will preserve some amount of supersymmetry. And by themselves, those smearings are not very easy to understand. It's just that they preserve supersymmetry, then you can solve the equations, and then you can get a lot of intuition.
Gautam, I think it's that the orientation of the D7 branes is not changed. It's just their origin. I mean, if you think of it this way, that the whole D3, D7 system is a point in a transverse R2.
Correct.
So you're just maintaining that split. We're just choosing where you are in the transverse R2 in an S2.
Okay.
So then of course
So then the preserved supersymmetry that
same.
is the same.
Yeah.
Okay.
Okay. Yeah.
Okay. Good. So now let me tell you something. Let's forget about the flavors branes completely. Just focus on the string. So this is going to be something. This is going to be the source term, if you like. That's the usual motor term, and we treat that couples to some 8 form, and this 8 form is essentially, as you can see, this basically encodes the fact that the strings are smeared everywhere, along the x directions and along also the compact 8 minus p dimensional manifold. Right. So if I start with this source term, if you like, in type 2 and type 2 supergravity, we know that type 2 and type 2 supergravity that has solutions, these dp brane solutions. Now with this source, you can easily show that asymptotically, there is an asymptotic expansion, or there is an asymptotic dp brane geometry in which the corrections, so this nq, if you like, is proportional to rho, where rho is basically this, and that becomes the number of strings or density of strings, if you like, in the large charge limit. So proportional to that, there is a correction which falls off as 1 over u, and u large is essentially the u limit.
P is the extended flavor brane.
Where P is the original P of the dp branes. So
brane, but why is the back reaction due to the flavor branes?
no. So the flavor branes are completely gone now. Now I just
charge.
have
You have a charge. NQ is the amount of
right? Yes. NQ is here.
That dies out at large U.
That dies out at large U. Yes. In other words, it does not destroy the asymptotics. If you like. That's a good thing in the sense that
in the limit where NF over NC is not going to 0, that's still the case.
So right now I don't have any NF. I just have NQ. But NQ is of the order of NC square. If you like.
The flavors will be proportional to NQ. No, am I wrong?
No.
I thought so the number of flavor branes would have been NF, and now you're turning. So
and then there is a charge.
This is new. This is what this is.
This is the rho. This is this thing.
But it's not. Isn't it the chemical potential dual to the flavor number?
Chemical potential dual to the flavor number.
No, it's chemical potential due to the fundamental string. It's like
yes.
What is that for the original problem?
So it's the same thing, right? I mean, so when we have this flavor brane, in other words, if you like, we are introducing quarks, Of course, but the understanding is that
UN is the UN.
Okay, that's what I'm saying.
I'm sorry, you want
I mean, that's what I'm saying.
But I'm just saying it's not counting the number of flavors.
It's counting the number of quarks, no? It's not the chemical potential which counts quarks.
Counts the potential that counts the number of fundamental excitations on the right quarks.
Quarks, right? I mean, you have either NF or NC, so you're counting number of quarks.
yes,
Right?
yes.
So what I'm saying is that so this is the chemical potential dual to that,
Right.
to number, and in that limit, even when it is so order whatever the other fluxes, that reaction is
Asymptotically
that of
it's
dominated by just the underlying
underlying original geometry, if you like. But it already tells you. I mean, of course, P is less than 6, assuming that. I mean, which is what we are going to assume always. So
So this omega, this funny symbol 8.
Oh yeah.
Whatever it is, what sets that volume for?
That's a choice at this point. So, for example, you could try to say that I am going to solve this problem with this supergravity with the string sources, such that I want to preserve some supersymmetry, and that could fix this side.
For instance, in the D3, D7 case, just preserving isometry.
Preserving isometry will fix it. Symmetry. That's the short answer. So from here you can immediately see that this asymptotic structure is not destroyed, even though you can also read that it would be a radial scale or equivalency and energy scale. Well, this term will become order 1, and then this geometry will really start changing. Right. So that is what this structure tells you. The point is essentially it's very simple. If you believe in gauge gravity duality for TP branes, it just tells you that including strings, we did not do something drastic towards that. We can still do that, but this is a particular follow-up condition.
But just to ask you, sorry, here you're working with the string picture, but if you had the underlying flavor branes, if you went out sufficiently far in U, then the flavor brane should kick in. Right?
Indeed.
So this is only an approximation.
This is an approximation. If you like, if I keep both, then there will be 2 terms.
But let me ask you more about Sandeep's question. We've got this fundamental string charge that extends all the way to infinity. So this should be thought of like a normalizable deformation. Right?
Well, that's what is confusing me, but it seems to act like that.
That's
it seems to literally act like a charge. That was your point.
Well, it's not quite ADS. I mean, this is the.
Let's take that.
If you take ADS,
so suppose we've got these D3 branes and we've got ADS space, and we put in this fundamental string charge. Is the point that this energy density is so small at infinity? Yeah, sorry, I'm sorry, this is some elementary thing. But the question is that, we know the finite energy configurations in ADS5 don't destroy the asymptotics.
Right.
But now you don't have a finite energy configuration, right? Because you've got a finite energy density and it's going all the way to 1. So that should be doing something to the function. I mean, we should be able to see that it's not a finite energy configuration, right? Is that correct or am I saying this? I'm not sure.
Well, I think. Well, okay. So the answer to your question is yes. I agree. It has to do something to the asymptotics, and this is what it does in the sense that it doesn't really destroy, but it keeps the asymptotics and it gives you a radial scale at which this energy will kind of dominate. I mean, your ADS is going to be deformed in the IR, not in the UV.
No, but that's what I wanted.
That is,
the energy extends all the way to the UV, right? Or not?
Energy. Well, I think if you calculate, it must correspond to the fact that energy has to be going to 0. I mean, you're not really changing the asymptotics.
Should it be that you have something which is in between a point charge and a fully extended brane in the 3 brane directions? If it were a point charge, its energy density would go to 0 because of the expansion of the volume. Here it's extending in one direction, just the radial direction, right?
Yes.
So maybe it still dilutes away.
So it's
now you're smearing in
it's
the
extended everywhere.
It's extended everywhere. It's extended everywhere.
It's a little more mysterious.
But it is extended everywhere, but at the end of the day, you really have the density that is factoring into it. I mean, of course, I'm dividing by the factors of Minkowski volume, which is infinite. That
and some of the factors that the sphere is growing very big. The energy density is probably the best. Right? Because of, I mean, let's say that the field theory volume was V, and you have the charge per unit volume is Q. That the proper volume is going to zero and it's going to infinity and infinity. And so the proper energy density is going to zero.
It probably has to be something like that.
But can I just understand, in the case that P was 3, is this like normal energy density, or finite energy in the bulk gives you 1 over R to the 4 forms in the metric? Is this the same for log or is it faster? I can't.
So this is essentially, let's see, that might be a tricky thing to answer. I have to know what this is. So if I directly substitute P equal to 3, then this becomes 1 over U cubed.
And what is U?
Not exactly, yes. So I would say that this is the same radial coordinate that you have in ABS.
1 over U cubed. Okay, that's interesting. So it's not quite a normalizable.
Normalizable definitely.
Yeah.
I see.
Oh, I see what your conclusion was now. Okay, I see.
No, suppose I was looking at only the G naught naught.
Yes.
To figure out about the the energy density really at infinity. So I would have had 1 over R squared because of D3. And if it was really D7, then I would have had log R or something like that.
Yes, something like that.
Yeah. Now I'm smearing these things. So I see. So you're saying that the smearing is making the log R into 1 over R cube, or no? So this is like going like 1 over R cube.
This is going like 1 over R cube. Yes. Also, this is not purely coming from the flavor. This is flavors with charges where the flux is very large. So if you like the brain, the log R behavior will only appear when you actually see the flavor brains. But when I have completely decoupled, so think about it, for example, the flavor brains are so far apart that I don't really care about where they are. And all I see are a bunch of strings. Yes, they do carry a signature from the flavors, which is somewhere hidden. But explicitly speaking, all I see is that ADS geometry is being sourced, or there are additional sources, gravitational sources, I mean, which are essentially just a bunch of strings. And they are far at infinity, they are just stuck with something.
And we have this 1 over R cube.
They have this 1 over R cube form, yes. Okay. So, alright, so let me proceed. So now, as I said here, of course, this already gives you an idea for a
Just a comment. Suppose you had a minimally coupled scalar field like the dilaton at infinity, and you turn on a non-normalizable mode of the dilaton, but keep the non-normalizable mode of the metric 0. Then you can so that also is turning on energy density all the way. And you can ask, what does the behavior metric look like? If I remember right, if I remember right, this is 1 over R.
Where in the
Okay, I see.
what is the point? So you have some scalar, massless scalar?
So let's say in the absence of the massless scalar, there are two behaviors. There is 1 and 1 over R to the 4. Okay, 1 over R to the 4 is the response to some finite energy, and 1 is really changing the metric energy. Now suppose you take out a massless scalar like the delta, and then you turn on non-normalizable mode for the massless scalar, but not for the metric. So there's no 1 turned on for the metric. But yet, this non-normalizable mode for the scalar propagates all the way from infinity down. The scalar is carrying energy. So it's constantly sourcing the metric more than a finite energy excitation. Okay? So it should source this thing you would imagine somewhere between 1 and 1 over R to the 4. And I believe it happens in 1 over R. Definitely 1 over R squared. So this is how similar.
I see.
I remember that it does happen.
Yeah.
But it doesn't destroy the answer.
It doesn't cause a 1 system.
Doesn't yes. It's going to do something in the at some point. So, and that is the next point. What exactly is the infrared? Because you can from here already see that at some u this is going to be order 1, and then we have no idea. So it turns out that this entire system actually has a solution which is of this type, this hyperscaling violating Lifshitz type background. So very strange name, I don't like it, but it's hard to express. But okay, so the basic point is that the metric looks like this, and of course here I'm completely forgetting about the compact part of it. It's not really relevant. But okay, here they are. I mean, it's basically the part. And everything is written in terms of P. It's a little generic. So what I want, I would like to draw your attention to one following fact is, for example, this, which is visible from here. So the dilaton has a factor of q to some power, which in the limit q going to 0 becomes singular. And q, if you write it in terms of a known parameter, it's basically the string density over n squared. Like. So this infrared geometry, if I take a density very small limit, is completely invisible in a quadratic frame. So this is something which you have to obtain by solving full equations. There is no other way. In other words, this is a non-quadratic solution, but the non-quadratic thing is in the non-quadratic parameter is q. And of course, so this hyperscaling violating Lifshitz type geometry, they come with two exponents. One is called Z, the dynamical exponent. The other one is called theta. It's called hyperscaling violating exponent, I think. And as I said, everything, you should just, even though I'm writing formula in terms of P, you should just take it as P from up to 4, not beyond that, really. So, so this Z and this theta, theta is completely fixed in terms of P, where P is the dp background, the original background. And if you're worried about what's happening at P equal to 4 from these two expressions, especially, and the others, the answer is there is also simple geometry. And let me just flash that to you.
Yes. Go back. I haven't. This transparency hasn't happened yet. Can you, for instance, give one example of P? So
suppose P equal to 3.
P is equal to 3. Okay.
Which is the.
So now this R power is positive.
The R power is positive.
Which means the dilaton is growing towards the U.
The dilaton is growing to, yes, that is correct.
Okay, and the Q power is negative.
And the Q power, you mean this one?
Q to the power.
Yes, yes.
So 1 over, it's like 1 over
to
square root Q or something.
1 over Q square.
Q 1 over Q square, fine.
Yes.
Which means that how fast the dilaton is growing towards the UV diverges as Q goes to 0. That's what you were saying.
That is right.
Why does that happen? I mean, should Q goes to 0 recover the original area?
Wait, that is not readable from this one.
Order of limits.
Yeah.
That's what happens in these new
So there's a small, what will happen is that only very small part of ADS is this thing. Where this thing takes over.
Exactly.
Shrinks.
Yes.
I see.
Yes.
I see.
And indeed, there will be flows that connect the asymptotics towards such things.
Okay, so there's a new region nucleated in your geometry,
Right.
and the dilaton has to match across the boundary of this region.
Precisely.
So the dilaton grows towards the UV, which means that it decays towards the IR. So the way I should think of it is that the dilaton is what it was in ADS5, and then it decays towards the IR.
Precisely.
And how should I think of this Q factor now? I should think of this Q factor as saying that this Q is telling me the position.
The position at which
which this matching happens.
Yes, precisely. Yeah.
Because we know that this dilaton is to equal the ADS dilaton
Exactly.
at the matching.
Exactly.
By the way, just out of curiosity, can you literally map this to an Einstein dilaton Maxwell system?
No, I don't think you can because there is
an
DBI.
interesting example where the same geometry.
Yeah, and this is square root type action.
Yeah, it doesn't look the same.
No. Okay, and for P,
you could translate that thing into a formula for the matching point.
Formula, yes, indeed.
And just to get a sense, that matching point always goes to 0 as Q goes to 0.
Always goes to 0 as Q goes to 0, yes.
Irrespective of what your P is.
Irrespective of what. Yes.
It should roughly be where that extra contribution is there.
Exactly, actually, yeah, precisely.
Say that again, what's the extra?
This thing.
This should become comparable to that.
This becomes comparable to 1. That gives you essentially. Precisely. And it's actually kind of funny because you would expect an Einstein equations being such complicated things, but it turned out that whatever you read off, the physics you read off from the leading order correction, essentially everything. I mean, other than of course the explicit construction.
And wait, sorry, just translate again. So now you're saying that you have found an exact solution.
Yes.
No, it's just the end point.
It's the end point.
IR attractor point.
Yes. It's an attractor. Yeah. I can use that.
Right.
So and for p equal to 4, there is a special one, but it's just a warped ADS2, just to say that there is nothing. It's also a very very nice geometry.
If you don't mind, can you translate once again? That's the
Yes.
exact solution I need. Okay.
Yes.
So this is the kind of thing Sandeep has been studying a lot, right?
Yeah.
Okay. So these are these things with hyperscaling values.
Yes.
Mhm.
Yes.
With the different exponential spaces.
Right.
That's what you're saying.
Yeah.
That's what Z is.
Exactly. And there's an additional this theta
Yeah.
factor, which is that it doesn't actually have a scaling asymmetry.
Yeah.
Very wrongly called hyperscaling violation.
So that's what's all.
Because this is actually the water identities don't satisfy the water identities of scale invariance in any sense whatsoever.
Yeah.
But anyway.
Oh, it's very interesting. So this system has a nice, interesting exact solution.
Exactly.
Very interesting.
Sorry to.
Yeah.
So I need to understand how this matching thing is done. I mean, so it's growing as r to the power 6 in case of p equal to 3, let's say. So it's a 1 over q square times r to the power 6.
Yes.
And then
you know
outside of
ADS
this near region,
You have ADS.
way down there, it should go as 1 over r to the power 4.
No, it's just constant.
No, it's dilaton is just a constant beyond a certain scale.
Yeah, so constant,
It's just
constant plus 1 over r to the, so constant.
Constant.
So now it's constant, and then it's growing in some way from UV to here. I mean, sorry, but yeah.
So there are so first of all,
So I'm matching this with the constant. Is that? I'm
Yes,
matching it roughly.
roughly speaking, yes. But also the UV radial coordinate and this radial coordinate does not need to be the same thing. Right? So there could be, in principle, a non-trivial matching between the radial coordinates.
So that doesn't matter. You just in the radial coordinate, where you reach that constant is the matching point.
That is correct.
It's not quite constant, it'll be constant plus fall
Yeah.
offs and all.
Yes. But yeah. But
I mean,
but leading order.
That constant is that order 1 over n.
The constant order 1 over.
The dilaton is the better.
Remember.
In the background of ADS factors, S times is 1 over n.
I don't
This I actually don't remember.
I mean, 1 over n meaning.
I mean, it's g squared n. Or maybe it's a different
No.
order.
At least normally I put it as order 1.
Yeah.
So you just take away 1. Okay, fine. So,
Yes, it depends on how you normalize it, right? I mean,
And here-
you factor of GS or not.
so at the matching point, what is the value of this? Is it 1?
At the matching point is this one. This I actually have to do. I don't want to say something.
Gautam's calculation would suggest that matching point happens at RQ equals Q.
Yeah.
Is that correct? And that's the question.
I think that is correct. That has to be correct.
Can we go back to the U formula?
Yeah. Oh, sorry.
So when these two are equal, is R cube equals Q? R cube is good because there's U cube.
I think so. I think so. But I have to.
I just said, where the dilaton becomes 1
Yeah.
is his new R cube coordinate equals Q. Now I have to check with your criteria.
I think so.
Although this may be another R coordinate.
No, but it's
Okay.
But morally speaking, I mean, if you are in ADS,
It's more or less the same.
Yeah. It's more or less
Okay.
the same thing.
Okay, thanks.
I think so. So, okay. Any more questions? Because I think this is, I don't know how long should I.
You can keep going. You can keep going until we run danger.
Until people start disappearing.
Until lunch starts.
That's a 1 o'clock.
That's a very large cutoff. Almost 50. So, okay, so, yeah, what did you want to say here? Okay, so this P equal to 4 case. Doesn't matter, it's all regular and it's a nice ADS.
Are these supersymmetric?
No. These are not supersymmetric. Okay. So just one slide on this hyperscaling while relations thing. essentially this is the form, this is the, you know this, but I quickly go through. So what happens is if I scale time and spacing in different ways with the lambda to some z, I completely touch it if you want, where z is called dynamical exponent, and essentially what happens is this length element squared that scales with some power of lambda, which basically gives you this non-trivial theta, which is not equal to 1. And if you want to understand in terms of physics, all it says is that you have broken Lorentz symmetry because time and space are fitted on different footing. And also this non-trivial theta implies that the entropy density, for example, will scale as temperature raised to P minus theta over Z. So P minus theta appears like an effective dimension. So the hyperscaling exponent theta somehow goes into defining your effective number of spatial dimensions. That's a physical understanding. However, there is a problem, as always. The problem is that such geometries, they lack typically infrared completion. What happens is there is either curvature singularity or infinite tidal forces, something or the other goes wrong.
You heat it up.
You can hide. These are good singularities.
Only a temperature with scales like
that is true. That is true. But these are all good singularities. That's also a good thing. But I want to mention that it's by no means. I don't want to say that this is an exact. There's no pathology to say. Okay, so connecting the flows, and this is the story, pictorially speaking. So we start with this UV.
Let me ask you: is it a stable solution in the sense of in any 3 grains, 7 grains? Is the solution stable?
You want to study fluctuations around it? Or
yeah, I mean, I want to know whether it's really the end point.
Yes, so in some sense, actually, we don't want it to be stable because if you remember our initial motivation,
yes,
so you want that somehow it to be unstable or source some sort of instability.
So you're thinking of this as the Fermi.
No, but I thought what you meant was heat it up enough to get rid of the curvature.
Yeah, let's do all that. Yeah.
After that, is it stable?
Oh, after that.
I mean, that's very hard to
I don't know.
But sometimes you hope it is. In simpler systems, at least.
Here, there are so many fields turned on. I mean, I didn't even attempt to do these fluctuations around it.
But if you only look at configurations that preserve your large isometry, then it doesn't sound so bad.
It's possibly tractable, but I have not tried.
Okay.
Say something I yes, so here the story is simple.
Sorry, just to understand.
Yes.
This color here along, basically you first think of it as the quarks building up a Fermi sea. I'm just going to check stuff. Think of it as the quarks building up a Fermi sea and then condensation, the superconductivity condensation around that Fermi sea.
Yes.
That's correct, right? So, are you saying that this should be the analog of the Fermi sea? And then the instability of this would give you the drive so
that would be the hope.
That's
I don't
what
know if I would, yeah. I don't have anything to back it up, to be honest.
That's interesting.
Because it's.
I mean, what you suggest is very interesting. First, that UCD at finite density will form a non-Fermi liquid.
Yes.
Because of this hyperscaling violation. And then after that, we get some analog, maybe of color theory.
Yes. That is roughly the ballpark of the hope. But yes, whether that works, it's. I mean, this system is actually sufficiently complicated technically. That's the problem. We can have supersymmetry. It's a bit of a nightmare.
It is nice. You have this exact.
But there's an exact solution, and you can also construct the flows numerically, which turns out to be not too difficult, but it takes some time. And of course, you can connect this UV data with IR data, etc. So let me take a summary here, and then I will quickly maybe summarize what happens. So far I've been talking about it purely in terms of when there is a very large charge, in other words, just string sources, nothing else. So the story is as follows. The UV is the d-dimensional Yang-Mills theory, which is a Veneziano type with order n squared works. And then what you see is that there is an infrared scaling geometry of this type with some fixed exponents. Of course, this symmetry is not easy because there are other fields which break. This is just the symmetry of the metric, but they are quickly broken, if you like. And the one comment I want to add here is supersymmetry didn't really play any role here. All that was needed was just to have enough symmetry which will allow you to solve the equations, which will allow you to have ordinary differential equations to begin with. And this side comment, if you start with, so far I've described as DP branes and then sourcing those geometries with strings. Instead, if you put, if you wonder about, for example, theories like ABGM, then also what happens is that such solutions are there, but they are asymptotically reached. They are not exact solutions. So you can go as close to them as you want, but you can never really reach them. That's just a point.
I see, but in ABGM with nothing, when you say ABGM with Nanbu or
ABGM with string sources, yes. I mean type 2A version, whatever you call that, ABGM. Yes.
Okay. You can get Suzy in some cases?
In some cases, you could probably, yes. Yeah. But this is sufficiently generic that you don't really have to bother about it. If you teach your generic features, then you can see it.
So just let me understand that. This if you have a 3, 7 and fundamental string system, these things presumably don't all preserve the same supersymmetry at the same time.
No,
they don't. So the original configuration, before you take some near horizon geometry, is not supersymmetry preserving ever.
Yes, that's correct.
So you would imagine that some sort of tachyon condensation or something has to happen before supersymmetry can be revealed.
He's just, in the region he works in, at least he's just got the fundamental
You're saying you just ignore.
Yeah, then further on, the fundamental strings and the 3 brane together could sometimes preserve Suzy.
That is possible. But everything together
but you're not now when you're solving, you're not keeping the flavor.
So far not.
That, right?
So far not, yes. Indeed.
Okay.
Indeed. But once you take that into account, then supersymmetry is
But then supersymmetry should automatically be preserved, right? It should be one or the other. What is this sometimes?
Doesn't
no,
the
you cannot preserve.
these fundamental strings don't preserve, are not compatible with the one? Maybe as classical. I don't know what this F1. It's the D1. It's the D1.
You know what's happening?
ND, what is that story? If you had a F1 transfers to the D3s, it doesn't preserve it, right?
No, ND is just before. ND is the relative transverse direction system before. So like that is how the 3-1 also works. And then the fundamental string, ending up and. But the question here is 1, 3 and 7. Whether
without the 7 isn't the 1, 3 where the 1 is transversed to the 3?
Yeah.
Preserving Suzy.
1 is transverse to 3.
But I think
so that is how you get ND
No, but I don't think
sorry. ND counting is for D.
Yes.
See,
so it's a string, so I don't know.
I see. We could check this as follows. Suppose you had it was preserving supersymmetry, the energy of the configuration should be that of the D3 brane plus that of the string. But now suppose the string were to go inside the D3 brane. We know what it does. It becomes flux.
I thought a string is transverse, isn't it? Because it extends in the radial direction. No?
Yes, extends.
And the 3 branes are point like in radial. So that's why I thought ND plus D and whatever is 4. No?
Yeah.
But just one more thing about that. If perhaps in one direction, but then he's smeared. So this is coming in every direction.
Oh, maybe that's what is it.
That might be it, right? Because this would break symmetry. So to pick out a direction in which the string is coming.
Actually, now that you say it, I think there is an example in which if you preserve supersymmetry, you cannot completely smear the strings. So that
makes sense because the number of supersymmetries you preserve is tied to which direction.
Yeah. So if you preserve supersymmetry, then it's partially smeared.
Good.
Then it's a partially smeared configuration.
Okay.
But again, in there, the good thing about this is this infrared is still there. So that there is still an infrared of this type.
Non-Suzy cases.
No, even in the Suzy case where you partially smear. Okay. So now, instead of the D3, D7, I have to unfortunately talk about this D2, D6, which is slightly easier in some sense to deal with. So what we have done so far, we have completely ignored the DBI action, if you like.
But your Lifshitz hyperscaling duality exists for D3, D7. Any of those P's?
Any of those P's, yes. Up to 4. Actually, you can do much more complicated thing. You can take these bound state solutions and source it with strings. Even then, there are these type of solutions. So that's a separate story. Okay, so again, what you have to do is there's the D2 branes, they're extended along D, and then a 2 spatial direction, and then there's some compact 6 manifold and radial direction on which they're localized, point-like. And what I do with D6 is they are obviously extended along E, R, and X directions, and it wraps some omega 3 within this, and by dot I mean that it's smeared certain way.
So what are you doing now?
So now what I am doing is I want to take into account the fact that there are also flavors, not just not the infinite charge limit. I'm trying to go away from the infinite charge limit. So if I do that, then I have to start with this configuration, and on top of that, what I have to do is on the world volume of the D6s, I will excite this.
So just one thing. By the way, if we really had a fundamental string between 7 branes and 3 branes, just in one direction, that by itself would be supersymmetric. Because just be the W or the
it would be 7 and
suppose we really had 7 and a 3 brane, and given your dilation, which I was messing up, I think that would have
When parallel D 3 and 7 and fundamental string.
That would be one of the supersymmetric matter fields.
Yeah.
So that by itself would also be supersymmetric if you really didn't do the same.
So very briefly, I'll just very quickly go through this. So what we have? We have this usual background, quote unquote, D2 branes, and they are characterized by these spleets, geometric, you have 4-form flux, you have a dilaton, and so when I have absolutely no density, in other words, just the flavor branes, no flux whatsoever, what you have is essentially DBI with Veneziano written in a slightly fancier form in terms of calibration, etc. It doesn't really matter. But as a start,
can I ask you something? Instead of putting this on some cone and all that, why not just do Schwartz written thing? Or you mean, and then look at. I mean, maybe that's just a trivial version of what you've already done, because putting it on a circle doesn't change.
yes, I would appreciate.
I mean, I guess that's all that happens there.
No, but why do you need to go on do all these cones and society?
No, that's just a generic description. You don't have to. I mean, in the sense that you could just start with.
Yeah, because I know the D2D6, but I mean, the Sakai works also for D2D6.
Yes. Yeah. I mean, that is probably more of a language which you can use.
Anyway, so
I'm not saying
that it's your hyperscaling geometry, and what we learn about QCD you will come to again, or
we hope to come to it at some point. I'm not sure.
Fine.
I'm not sure if I can actually come to it.
Okay.
That's for the next talk.
So all I want to say here is, okay, let me not go through these things. It's not essential for the.
What is the code in this case? So you have nearly KLS structure. What's the underlying?
If I have if the base of the cone is just a nearly KLR manifold, which means and not just that, it also you have, in terms of structures, you have some SU3 structure, which means that you have a globally defined 2 form, real 2 form, and complex 3 form. So the whole purpose of that is that it will just allow you to write down the ansatz in terms of things which are globally defined. That's all, nothing more, because you need something.
But I mean, what is this? This is 2A with some.
This is 2A. Yes, this is 2A with 2A plus sources, where the sources are DBI plus withsources.
Right. But it's in an underlying manifold which is not a Calabi-Yau, right?
It's not a Calabi-Yau, right?
So it's obtained from a Calabi-Yau with some fluxes turned on, or what's the idea?
No, I think you're just putting.
Okay, if I check the back reaction that you're getting.
Yes, I mean, if I completely forget about the Calabi-Yau language, all I want to say here is I could start with a supergravity. So solution where I have basically 6 compact directions. And this 6 compact direction, this manifold is just a nearly Kähler manifold, which will allow me to write down the fluxes in terms of globally defined forms. That is all really I do.
Is there some, just as when Klebanov written or thereafter subsequent developments, you actually had a cone which you got by looking at the conifold singularity of a Calabi-Yau, right?
Right.
But here you're not doing that because that would have come with a Kähler form and so on.
Yes.
So this is, do we know how the cone arises in terms of simplifying, or you don't care? And
I mean, for the time being, I mean, it's not essential, but I think it's a cone over a G2. It's a what's the word? It's called the G2 holonomic cone, I think. It's not the Calabi-Yau. Yes. And G2 holonomic because nearly Kähler has essentially that structure. Yeah. That's indeed. It's if you like, it's the analog of the Klebanov-Witten type thing, but the base is Sasaki-Einstein. Okay, so anyways, and then on top of that, you can also excite gauge fields, etc., which corresponds to density. We will go beyond that. And you can start with an ansatz which is sufficiently generic of this form, which is also something that we considered before.
In this case, do these experiments destroy the geometry at infinity or not?
No, they don't. They don't.
This is just the fact that there's no asymptotic freedom problem.
That's correct. That is correct, yes.
Meaning that 7 branes have to destroy the geometry at infinity for the 3 branes, because we know that we add matter to n equals 4, it's not asymptotically free. I mean, it's the other. So, but here, 3 dimensions.
That's one reason why D2D6 is much easier, because then you don't have to worry about that. So let me actually come to that. So there are basically 3 regimes or whatever. So there is an UV which is still asymptotically true. It's not destroyed by anything, the density or the branes. And if you can view both these D6s and these finite density perturbations as subleading factors.
But the number of flavor branes is smaller than color, is it?
No, they can be of the same order.
But then why should the D6 battery actually be smaller? It may not destroy it, but...
No, it's smaller in the sense that it's not, okay, it's smaller in the same sense that there will be a radial scale at which it will become important, order 1.
I don't mean the fundamental.
So you think it will behave like the fundamental charge in this case?
Really?
Yes.
For why? It's extended in everything. The D6 brane should be as important as the D2, right? Am I missing something?
No, as important, but somehow this dilution is supposed. I mean, you could have said the same for the fundamental strings.
Yes. It's I think it's about how many codimensions you are in. Because D7s you can never, D7s always destroy the
But
asymptotic.
D6 extend in more directions than D2, right?
True.
If I looked at it from the point of view of a D6 and the back reaction of D2, then you would have said the D2 is growing in its back reaction asymptotically. I don't know, it sounds a bit weird to me.
I mean, naively, D6 would go as 1 over R. I mean, the D6 potential will go as 1 over R, whereas D2 will have 1 over R to the power 5. So even 1 over R will not destroy the asymptotic. I mean, there is no 1 that will appear.
But wouldn't it dominate over the 1 over R?
Yeah, the normalizable, so normalizable
But
mode
he's saying that D6 is subdominant compared to the D2.
that elements.
That's what I was asking. It seems strange.
Even when NF is
Yeah.
Well, they are.
Unless you're taking NF over NC to be not small in 1 over N, but still small compared to 1 or something.
I would not necessarily say that. I would say that the corrections that come are exactly of this form. In the sense that they have a 1 over U to some power. And then this coefficient will obviously depend on NF over NC.
There's one more thing to say though. Just, the pure D2 geometry is singular in the
Yeah.
So, I mean, I don't know from geometry, but I was thinking from the field theory. From the field theory,
No, it's because the dilaton.
Because of the dilaton.
The dilaton.
correct.
Yes.
But from the field theory, both the theory with the matter, and the theory without the matter, are both free in the unit. So, from that point of view, the singularity should become worse because you added it.
Yeah, but the nature of that singularity should be dependent on the 6.
You imagine singularity came at the same place because the singularity would just.
The singularity comes with asymptote. I mean, for both of them, very far away.
Right. But I don't think that you push it in some. You start with free quarks and gluons. The same dimensional analysis governs when the theory becomes strongly coupled. And roughly at that point, geometry should take over. It's very different. The field theory is very different in the 4-dimensional case.
Yes.
Right? Because it totally changes the UV beam. Adding these quarks.
Yeah, but if I just had the D6 brane field theory,
it's very hard to say, but because both of them were not geometry.
That I don't know.
But
that I don't know. That I don't know what will happen.
But
D6 brane field theory, then it will be more like the D3 brane compared to the D2 brane.
no, but we're taking
So
it's a different decoupling limit. The decoupling limit is one in which the gauge coupling of the D6 brane is just zero. The field theory that this is dual to has only gluons for the D2 brane, not for the D6 brane.
How does geometry?
Well, by the decoupling limit that you're taking alpha prime to 0 in a particular way, so as to keep the D2 brane gauge coupling fixed.
So will not convinced at all.
No, you can, when you construct the near horizon geometry of DP branes,
Yes.
if you had D6 branes, you construct the near horizon geometry.
Yeah, but you do one scaling of the radial coordinate if you did that, and another scaling of the radial coordinate if you were doing the D2 brane. The Maldacena arc over the U coordinate, okay, will be something for D2 branes, something else for D6 branes. And you're doing the scaling for D2 branes even though you have the D6 branes. So let's just think of it for a moment from the point of view of the field theory.
You just drop the bounds. That doesn't much matter. And then you look in R, and one thing falls as 1 over R to some power, and the other thing falls as 1 over R to some other power.
No, but there are alpha primes around. That doesn't matter. No, but the field theory we're looking at.
Alpha primes go with R to make up dimensions.
But the field theory we're looking at is one in which the field theory is 2 plus 1 dimensional field theory. There are no propagating gluons for the 6 branes. That would be a very different system. The propagating gluon. Maybe another way of saying it. Maybe we should go on. Okay. But I think another way.
It's harmonic functions with the role of alpha, with alpha primes coming with R's,
Yes.
and number of branes of the corresponding type coming.
Correct.
And therefore I'm saying, if you go far enough, the 1 over R from the 6 brane should dominate over the 1 over R to the whatever. That's how I was thinking. Maybe I'm wrong, but we'll see.
No, but could there be alpha primes left over?
It's just dimensional analysis. If one thing falls like 1 over R to the 4, there's an alpha prime square up there. And the number of 3 branes there. The other thing falls like 1 over R.
Yeah, so for D6 it would follow as 1 over R, and for
That's
D2
what I
it would
was
follow
thinking.
as 1 over R to the power 5. So it will come with N2 over R to the power 5 plus N6 over R. So that's what
And
I
the additional Maldacena is that there are constants, ones and all, and harmonic functions which you throw away. That's how I think of it. This is
If it was literally that, then you would be looking at the gauge dynamics of the D6 branes. I mean, the Maldacena limit in which you do, if you didn't have 2 branes and you just did what you're saying for D6 branes, would have the gluon dynamics of D6 branes. And that's not the limit we're taking. We're doing something different. We want to keep only the gluon dynamics of the D2 branes, and this should just be flavor. So that's, I don't know how it shows up in the scaling limit. I think it has to.
I mean, flavor branes, the gluon dynamics of flavor branes have to be included. When you have 7 branes in the bulk, you have 7 branes in the bulk. Their gluon dynamics.
No, but let's look at the UV theory. This is some geometry. It's dual to what? It's dual to some gauge theory, and in that gauge theory, the only gluons that are propagating are the D2 brane.
Yeah, that's true.
Okay. So, on the other hand, if you took the scaling limit for D6 branes, you would be looking at the UV theory in which the gluons that are propagating are the D6 brane gluons.
I'm just saying that the correct limit is that I drop the ones in the harmonic function and I look as a function of R what happens. because you're sufficiently close not to care about the asymptotics.
So there is some alpha primes left over. Suppose maybe we should just go on.
No, I don't have a good answer to your question.
Okay.
Other than saying that.
Even once in a new coordinate is not dimensionless coordinate. It's a dimension of energy.
Yeah, but you don't have to work in that coordinate.
But suppose
I work in the radial coordinate and look, my statement is about geometry first, okay? Take a D6, D3 or whatever, what was it, D2, D6,
Yeah.
geometry. If you like, solve the whole thing, okay? Alright, now come in close enough so that you can drop the ones. Now how close depends on which various brains you have, right? Okay, so first come in so that you can drop the one. Then it seems to me that for a while the D6 brain geometry, D6 brain back reaction or whatever will dominate the geometry, and further in the D2 brain.
But it could take a scaling limit in which that D6 thing is just gone, right?
You could do that. You could do that. In that case, I don't know what happens.
I think that may be the limit that will be good.
No, but then you're not sensitive to the D6 brain back reaction.
No, that I don't want to say that, because what will happen is,
See, then that is
non-trivial
here, for example, you've done that. You've kept the
Yeah.
gauge strings and not kept the 6 brain.
That's correct.
Then I don't have an issue. But I thought what you're doing
Yeah.
is, in addition, there is a further correction if you keep the 6 brain.
Right.
And that's what you're keeping.
Right.
And you still find that it falls.
Right.
And that confuses me. That's what was
That, yes. Yeah. I don't have an answer.
Okay, go ahead. I might be wrong. I see your point also.
Yeah.
I see your point also.
Yeah.
So I think maybe I should try to wrap up. Okay. What do I want to say? Yes. Let me just say this, and I'll just show you a picture. So this is the statement which I don't actually know how to explain now. Like this is it. This is what the calculations give me at least. Then of course there's an infrared, which is precisely the one that we had before, and then there is an intermediate range, which is just a pure ADS4. So if I just show you a picture,
ADS4 in some
yes. So the story is something like this. So if I have a two-brain geometry, in other words, the super Young's theory,
And obviously doesn't depend on which almost scalar or whatever manifold you choose.
Not necessarily.
Where did the information of that go?
Oh, that
you have a choice of many almost. I don't know anything about these geometries.
So that point into essentially these answers for So you have to put in various answers for various classes. So as long as I have those globally defined.
Is there an underlying metric for this code?
Yes, you can write down. I mean, for example, if I take S6, then everything is known.
Oh, okay, for SC, but I mean, if you change those codes, things don't change.
No, yes, that is correct. So I can take S6, I can take CP3, I can take something else. The story would be exactly the same, as long as I can write down the answers.
That's like those M-theory solutions which are like ADS4 cross Sasaki Einstein.
Yes.
And it's always that Sasaki
It's always
part which changes and like
Precisely. So instead of Sasaki Einstein, you have this nearly capable.
Here, depending on which singularity, it still doesn't change. There's some cone, there's a singularity in the Sasaki Einstein part, he's putting brains at that place, and he gets a fairly universal.
Yes.
Yeah.
Yes.
Great.
That's actually the good thing about this. Although, I mean, explicitly speaking, nearly Taylor manifolds, if you ask me, they're very that are known. So this is essentially the story. That we have super Young-Mills with this UV being D2 geometry, and then there is this hyperscaling violating, if you like, non-relativistic theory, and this rho, if I some fixed by some various parameters in the case, so essentially it measures how much charge I have. So rho going to infinity limit is essentially completely lose any information about the D6s, and then I start from here and go directly to this. But I can also keep tuning this lower and lower, and then I will trace curves like this till you realize that there will be a region which is almost conformal. You can, if I have a non-zero rho, I can never really take a limit in which this will go exactly there, but you can go arbitrarily close, and then eventually you have to bend backwards to this infrared.
Sorry, I was spacing out, but
So
what is this diagram?
This diagram is essentially represents the possible. So if you like, fixed points, quote unquote, in when I have D2, D6,
And diagram denotes geometry of the state.
So this is a geometry, this is a geometry, this is a geometry, and these are flows.
Are you serious? Are you telling me that fixed point is basic issue? Is some kind of a quiver theory with matter coupled to chance?
It seems to be yes.
Is it
If I have, for example,
people can assume I wasted a lot of time thinking about it. No, but I'm sorry, I'm just joking. But I mean, I didn't know there's a field theory, there's a gravity realization in
This is actually
It's a conjecture.
No. So there is, if you
No, but without Susie or anything.
yeah. Oh no, this has supersymmetry. This one has
This is already.
This
Okay.
one has supersymmetry. But
Oh,
this
I thought the good thing here was that we could do it. So these are all ABJM orbifolds, other
yes.
some Sasaki, whatever.
Some. So this part of it, if you like, does depend on supersymmetry to that extent. But I mean, if I'm talking about the entire picture, then supersymmetry is
Okay, no, I got excited because I thought you had known Susie.
Wait, just let me understand. Right? As you start with superangular, what is happening there?
So what is happening there is, suppose I have no charge.
Yes.
Just the D6s.
Yes.
Right? So in that case, all I have is a flow, which is actually, by the way, analytically known, and this is a supersymmetric flow, which goes from super-Yang-Mills theory to a Chern-Simons line theory, and geometry goes from D2 to AD4.
Yeah. So in particular, if you have D2s and no D6s also, that just goes to ABJM.
That just goes to ABJM. Yes.
And now this goes to ABJM with some flavor.
With some flavor, indeed.
Okay. And now what are these documents?
And then, so suppose I had infinite charge, so the D6s are completely gone from the picture. So this is the flow that I start from super-Yang-Mills theory, and I go from there to this infrared Lipschitz, whatever, hyperscaling, etc. And now I can have some finite rho.
Okay.
And as I keep tuning rho, what happens is the flow, if you like, it can, if I go to rho going to zero limit, it can go almost as close as possible to this conformal point.
Okay.
And then it has to eventually turn back to this.
Okay. So this rho is like an unstable perturbation of that.
Rho is yes.
Of that point.
Yes. Yes. So
What was the first thing? If you just took no charge, D2s and D6s, that will still go to ABJM.
that is the subflake here.
I mean, ABJM on some code kind of thing, right?
Yes.
Of
If you do it on, I think you have to do it this CP3 and then
some singularity of society.
singularity.
Well, we could just take D2s to start with.
You could, yes.
The simple case.
Indeed. So
Yeah,
what?
but even with D6s, that
So what happens is the number of D6s that plays the role of the Chern-Simons level.
What?
Yes.
Oh, you want the ZK singular? So here, I mean,
So-
normally it was the orbifold, right?
Just if you take D2s, just in flat space on
Yes.
with your Sasaki Einstein is replaced by the sphere of the right side, so
Yes.
S6. Okay, then this would just go to ABJ with K equals 1.
With K equals 1, yes.
And now you're putting flavor and that changes K.
So if you put flavor,
That's because he's changing D6, no? Isn't the D6 the orbifold in M theory?
This is something. Right.
The top
I see.
so the
I see. I agree.
yes. Yes.
Oh, so it doesn't give you ABJ with flavor. It has flavor